So this is, we've done all our crypto stuff. All the crypto stuff is really relevant for the steganography stuff. So I'll try and give an overview of some of the other methods that are really relevant. Are we ready to go? Yeah. Okay. Right, so for today, what we're going to do is we're going to look at steganography, which is really the art of hiding something in something that looks valid, that maybe has another purpose, but is inside it. That by looking at it, by statistically analysing it, you can't actually see what the actual hidden message was. So mankind has been doing this kind of thing for centuries, thousands of years. We've been passing secret messages to each other in perfectly valid forms. So we'll take a kind of random walk through steganography. We're going to look at some of the methods that are actually involved. We won the Cypher Challenge this year. Our students won that. So we were applying all the methods that we'll see here. We can applied as part of the Cypher Challenge, especially Charlie. So we've actually really did have applied a lot of this method. If you're given, like we got a picture of Alice in Wonderland from Raw Holloway, and we had to analyse that, looking at the least significant bit for the pixels and so on. So when you're faced with something that you have no idea what the code is and what it's set up, you have the challenge to be able to find out what the methods was. So we'll look at some of the methods, then we'll look at some of the discriminators. Discriminators are the little highlights that say, oh, I'm a JPEG. You might not think I'm a JPEG, but I'm a JPEG because there's an FFFD or there's FF something, or I'm a GIF file. You didn't think I was a GIF file, you thought I was a movie, or you thought I was a Word document because somebody hid it that way. So the discriminators are there to really identify little fragments so they can give us pointers to what the thing actually might be. So remember, you're not always going to get a complete evidence bag. You're going to get little bits of evidence, little bits of fragments, and especially these days, you're looking more at triage, which is basically just picking off little bits and pieces from a crime scene or from an investigation, and then trying to make some sort of sense of it. So we'll have a look at discriminators, and then we'll have a look at some covert channels, how Bob and Alice can speak to each other, and everybody's watching them, listening to everything they say, but they're actually sending each other secret messages. So covert channels, there's an infinite space for a covert channel if it's required. But we'll look at a few examples. Typically, network packets. You can hide lots of stuff in network packets that can't be seen by normal devices. But if you know where to look, you'll actually see where the data is. Then we'll have a look at port knocking. It's possible to set up a system. I knock on port 99, and then I knock on port 1999, and I have a communication channel. Only by knowing how to knock at the door can you actually get into the system. Then we'll have a look at a very scary area of onion routing. So how does Tor work? How does Tor hide how does Tor hide the identity or keep anonymity of the individual, of the devices, and so on? So in steganography, sometimes what you want to do is to hide the original source, the original person who created it, and so on. So have a look at onion routing. And on the way, I'll try to give you a heads up on the coding methods that are used in virtually, I would say, most of the areas around images and video. That's Huffman coding, Lempo Viz, LZW, and run length encoding. Okay, they're all in there as a little magic box, and they're all there as a kind of coding method, but they're there to kind of hide the original sort of information. If anybody sees any other things that we're missing off, then we could really go on for infinity, but we'll try to cover some of the basic principles actually involved. Okay, so there's where we are. So we've got things like covert channels in there. We can send. So if I stuck my hand up every minute to identify a binary 1, you probably wouldn't notice it. You go in there, blah, 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 and then I didn't do it the next minute, that's a 0, and blah, blah, blah. only if you knew that I was putting my hand up would you actually be able to. If I told somebody here every minute I was going to put my hand up, I'm going to send you an ASCII message and I'm going to convert it to binary, and I put my hand up if it's a 1, and then if it's a 0, you probably wouldn't notice because you're watching something else from there. So covert channels are all about the two people know what's involved, and Mallory, Bob and Alice know, but Mallory doesn't actually know what it is. Mallory is watching all the time. Mallory is our new person, Bob, Alice and Eve. Mallory is our new person who's the investigator, who's really watching Bob and Alice and so on. So we can have our covert channels, we can have a steganography with inside there. We can go for linguistic steganography, as we'll see later, or a technical one where we take images and we hide images within other images and so on. And it's not really too difficult to take an image and hide it within another image, as we'll see. We'll look at anonymity as part of our Tor networking, our onion routing, and so on. And then there's a large sort of area just now in copyright protection. How do you watermark an image? How do you watermark a movie so your network sensors can pick it up? Or if somebody has your content, you can say, it was mine. There's my watermark in there. So the watermark's there, that you don't see it, but it's there, and the person doesn't know it's there, but we can actually detect it. So there's a whole lot of areas that really are important with inside this. Okay, so this is what we've done. Okay, so all of the above are relevant in steganography and hiding, encryption, public key, private key, one-way hashing, and encoding. All of them are relevant with inside our steganography and our hiding. We can hide something as a hash. If you know how to unhash it, you have a rainbow table. That's a perfectly valid way. We can spot things like base64 easily, but a member of public probably couldn't spot, like we had taken the word hello and made it a base64 from there. But we know that that's there. We could put it in another language, another coding language. We could put it in a Japanese character set. And then all I have to do is to put it to a UK character set and the message actually appears. So there's lots of ways that we can encode the message and so on. Lots of ways that we can use encryption to be able to pass our secret messages. But there's not much challenge in that really. That's kind of easy. There's no fun in passing a secret message, like if it's all encrypted and things like that. So some of the methods with inside this area really are really tax your mind as to how they would be set up. And we've been doing it for thousands of years, ever since mankind really walked on the planet. We've been passing secret messages to people. Smoke signals, not quite secret. That's one way. If you don't know what the smoke actually means and the signal there, that's kind of secret too. And we see in the movies and things like that, used to have the briefcases where somebody would drop a briefcase, walk along and pick that briefcase up. That's a way of passing it. Microfiche used to be used a lot, where you could shrink down a document into a very small space, maybe eat it. It's not a very good method, but it's valid. You could maybe just put it as part of another object and so on. So you know where to find the microfiche, then it's fine. And then things like typewritten templates and so on. So it's really a method that's been used for so long. So can someone find that message? Let the mission begin. Okay, how'd you do that? Hello, hiya. Just watch the cable. Just watch the cable. We'll give you the challenge now. There you go. That's a secret message. Okay, so how'd you get that? Okay, so the first letter of every word. So now that you see it, it's obvious. Okay, but it's not quite obvious if you just looked at that. If it was on a billboard, You probably go past and you say, oh, that's fine, that's great. I don't understand what they're saying, what they're talking about, but there isn't. But if we know that, so that's obviously a simple method there. There is what's called the Bible code. There are some people, and you can watch the documentaries. Have you seen it? And they will go through the Bible and say, if we take every fifth letter in this in this passage, it actually says a message like Jesus will come to the earth and things like that. And there are people, and obviously if you take lots of text, you will find something like that there anyway. But some people say there are subliminal hidden messages in the Bible and in certain books and so on. So you can see there. So there you go. That's my contraband image. I've stolen that image, and really I'm at a border control, and I don't want to be caught with this image. So why don't I just slip that image on the top of it? My PowerPoint. Is it still there? Hello, are you still there? Is it still there? Maybe. Explain. Right, okay. It's 50-50. Does anybody want to give a definitive answer of whether it still is there, and what I mean by is it still there? You didn't think you were coming in a philosophy lecture, did you? Is it still there? Does it still exist? Did it ever exist? That's the question. What do you think? Still there.
You can only check if you open the file.
That's right. So explain.
At least maybe you just need to identify the file that is covering it.
Yeah, yeah.
Separate from
It's still there. Okay. PowerPoint is an encapsulator, just like PDF and so on. It bundles together a whole lot of things. You'll get lots of false positives. If you're looking for JPEGs, you'll actually get a lot of PDFs firing off with JPEGs. You know what's going on here? I'm looking for, and it's because those formats are encapsulator. The file's still in there, and it's still there, so it is there. It's just you can't see it just now. So I've hidden it. It's still there. As someone looking at that PowerPoint, we go, yeah, it's fine. I can't see that image at all. Oh. What's happened there? What is it? It could be white on white text. That's certainly. It's not white on white text. Sorry, what did you? What? Is it hidden? It could be hidden text. Yeah. So it could be hidden text. You're right. White and white. Standard. Get an onion, and get a pen, and then write with the onion ink, and it's like invisible ink there. I could have done that. That would have been fine then, and you could obviously analyse that. But where do you think it is? There you go. Right down at the bottom right-hand corner there. So I could make it 1 pixel, and you wouldn't see it. Is it still there? If it's 1 pixel on the screen. So there, it's there. Still there. Still preserved. Still the same thing. Still the same resolution. I just happened to make it 1 pixel on the screen. You see a lot of these dodgy tracking people now. You see, you ever get an image that's got 1 pixel in it? Have you ever seen that? You get an email, it's got 1 pixel. What are they doing there? It's 1 pixel. Are you going to see it? No, 1 pixel isn't quite subliminal. There's a bigger reason behind it. It's 1 pixel in my email, and they say, "Hello, Bill, how are you?" And it's a 1 pixel. I can't see it. Why do that? They do it on websites too. I've got it on. I can show you one of the pages. It's an image, and it says 1 pixel width, 1 pixel height. Why do they send you an email with a 1 pixel image in it that you're never going to see? Got to think like an adversary. You're thinking too nice. Why would I send you an image that had one pixel as an email?
some kind of editor you can decrypt it.
No.
Keep it hidden.
No, no. This is a really, really simple method of tracking.
Think of HTML works.
I stick it on my server, okay, so there's a little clue. I say, hello, how are you? And I stick it on my server. It's 1 pixel. What is that going to actually do? It's a spam email. I've sent a million emails out.
Someone click on it.
Not click on it.
It's going to verify that the email that they've used is a real one. So if they're generating them,
Yeah.
like
Yeah.
randomly,
Yeah.
anyone who
That's
it's your server then,
yeah.
that email is a
That-
genuine one.
That's exactly right. So I can make sure that that the image that's generated will link to the person I've sent it to. So for one, I know they've read it. For two, I know who it was, and for three, I know what time they actually read it there. So it can be used for that kind of purpose. So that was my one pixel. It wasn't 1 pixel, but it could be, and I've just hid it, so nobody would really find that. But if we look at it, so that's a picture of my ex-cat there, long since deceased, Cookie. So there's a picture of Cookie. That's my contraband image in there, and there's a PowerPoint. But if we look at the binary, so we often end up in the hex, the deep dirty hex in there. You can see it comes up with the name of the file and then all the details. So all the copyright information, all the metadata comes right into PowerPoint. It just happens that it's got every second letter. So it was called Cookie Pictures Transparent dot something, but it's missing every second letter. So that's like a P00, I00, 6300. So what's it done? Why has it done that? Why is it mucked up? So my picture was called pics underscore cookie blah 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 dot gif. But if I search for that on my disk, it's not going to find it. What do you think it's done there? What translation has it done? How many bits is ASCII? 8. It's 7, but 8 now, roughly. And what's the problem with ASCII? ASCII's great. What's the fundamental problem of using the ASCII character set? It's limited. It's limited. So we need a lot more. We probably need 16-bit. Anybody know the name of the 16-bit one off the top of your head? If you can remember. It's okay. I know it's early on a Friday. But the standard one now is 16 bits. Your character sets, your ISO character sets are 16 bits now, which means that ASCII gets represented as 00 something something. Does anybody remember, this is really sad and is really geeky, but you might get this as your £1 million question if you're on Who Wants to Be a Millionaire. What is the hex for a little a? Remember one of them, if you can. What? 48. 65 decimal or 42 hex. What's the difference between a little a and a big A in the number of bits that change? What? No. I don't know where you got that from. I'm not going to think about that one. 13. It's 1 bit. It's 1 bit. It's 1 bit. 1 bit changes, and that's it. Anybody know why it is 7? They used to have ticker tape machines. That's how they used to do computer programs, and the tape was obviously a certain width. And if they did 8 characters, the tape would actually break, and they could only do 7 at a time. So that's where all this goes back to, and we're still kind of using it from those days. So this is what's called extended ASCII, and is a 16-bit character representation. So your nice little 8-bit characters don't come out. So when you're searching on a disk, you make sure that you search for 00 and then something something 00 something something, and that's the binary string that you find. But you can see there in the PowerPoint, my image is still there. It's not gone, it's not been trampled, it's not been converted into other format, and so on. That is different from the new format. What does the new format look like for Word and PowerPoint? Does anybody know what it is? So I couldn't really view that in the new PowerPoint. Why? What's a DocX and an XLX and all the other ones? What are they? What are they fundamentally? Well, there's zip files. If you change a docx to a .zip, you actually find it's a little zip file. PK is the standard header that you look for now, which means it's compressed. So you won't be able to find that until you uncompress your Word document and so on. Okay? So we're increasingly compressing things, and you won't be able to see that. One bit change will change the whole of the compressed bit stream. So these are some of the methods that we actually use in terms of our steganography. We use a noise. So every file's got noise. It's got something in there that really isn't doing very much. There's lots of ones and zeros that really aren't that important. If I've got a 20 megapixel camera and I'm looking at it from afar, 20 megapixels is just crazy. I'm not going to see every single pixel. You'll be lucky if I see like 16 pixels brought together. If it's afar, who cares? I can just see the skin tones and things. Your eye is much more sensitive to changes of light, lightness and darkness than it is to changes in colour. So there's lots of noise within our files. From a steganography point of view, we can hide stuff in the noise because it's not going to change the files that much. I can stick, if it's a 20 megabyte image, I'm just going to chuck in a few pixels. You're never going to see it because you never see a pixel that small. I mean, the way phones are gone, it's just crazy now. I mean, there's no way that your eye can actually see it. There's no way that your ear can actually hear high quality 24-bit stereo. You're sitting in a place where there's reflections and so on. So there's imperfections in how you're viewing things, and you can hide things with inside there. You can spread the information out. So every day I could send you a message, one message a day. So we can spread the message out, and your IDS system is just going to forget about the track and so on. So by spreading the information out, like if you're doing a Hydra attack or anything like that, you spread it out, and it takes it longer for a device to be able to detect it. We can define a statistical profile, and the statistical profile is a bit like what we saw before with let the mission begin. I can make it look like it's statistically relevant. Everything in that message, hello everyone, and leave lots of opportunity. You look at that and you'll go, that's fine. Statistically, that looks like a message, it's okay. But only when you look at it, you see H-E-L-L-O, hello. So the message is hello, but I've hidden it because it has a statistical profile that a computer or you would say that looks like standard ASCII, that's standard thing. Then we can define a structural. So we can send each other a message. So I've got some football scores there. Manchester United 0, Manchester City 1, Celtic 1, Aberdeen 0, Liverpool 1, Stoke City 0. They always got to go down or up, and then it's Hearts 0, Hibs 0. Okay, that looks okay to you. You look at that and you say that's soccer, football scores, everything's fine. What have I done there? It was a low-scoring day, really one of the most boring days of football, probably ever. Really dull matches. Look, yeah, so it's the letter H that I've just sent to you. H ASCII is 0, 1 1 0 1 0 0 0 0. Okay, so I've just sent you a message, But as far as you know, that looks like football scores, and you would never know that I just sent you a message in there. I can change the order of things. So we have a shopping list. I just change the order of a few things, and you can spot that, and then we can actually see that I can put the message in. By the minute it's places that I maybe move something, you can stick in a message there. You can split the information across lots of different packets or lots of different pages, and so on. And then you can obviously hide the source, like an onion routing. And you probably wonder why David Bowie is there. If you took David Bowie's freckles and then give him freckles, so let's say we're going to put freckles across his brow and then down on his chin. So as far as you're looking, they're just little imperfections in his image, but I know where to look, and I'll see if he has a freckle here and here, and then that's a 1. So again, that's an H that I've actually transmitted. Obviously, you would make it look as if it was spots or some imperfection within the image you wouldn't actually see in there. So we can replace randomness, and the eye would never actually know them. So let's take the example of JPEG hiding as a case. So I've actually hidden a message in that JPEG, and you would never know. Can anybody see the difference there at all? No, it's impossible. It really is impossible to see it. So I took an image and I embedded text, and you can't see the text in there. And how it does it is that most of what we have in images is low frequency. If you were to zoom in right into an image, right into it, you'd actually find there was very little variation in the pixels. Okay, even a photograph, if you zoomed right into the pixels, right into the skin, you'd actually find they're all roughly about the same color, not really that much. So what they do in JPEG in most image compressions is they do a frequency analysis or spatial analysis. Spatial analysis analyzes the change. Okay, just like you've got high frequencies, low is a high frequency, and low is a low frequency. They do that in images. So something that's changing lots in these little pixels will be up at the high end, and something that's low, not many changes at the low end. And most images, and this is how the compression works in images, this is why you take a 20 megabyte image and you can compress it down to 100K. It's because of this. And really when you do an analysis, most of it is in the low frequencies. And very little is up at the high frequency end. Very little, when you zoom into an image, you'll see lots of pixels changing very rapidly. So what we can do is that we can actually stick in our message up there. So we stick a message up there, then you're not actually going to see it because that will be high frequency changes with inside. When I've zoomed in, this is the message embedded. This is hello, how are you? And you can just see the slight change that I've made within the image, but you would really never tell that I'd actually put that in there. So let's look at discriminators. So how could we find out if there was something embedded into some content? How do we search? What are the things that we have to search for? Okay, so there's our photograph of Napier's Castle there. And what I've done is this is how it takes the image. So it takes each pixel block, 8 by 8 typically, and it'll take each block and what it will actually do is take each block and then do that basic frequency analysis of it. Okay, so when you're watching a movie, when you're looking at an image on a screen, actually this is how the image is actually stored. It's not stored as a bitmap. Why? Why do we not just store everything as a bitmap? How many colours do we normally have with our images? And what are those colours? 3. And what are they? Red, green, and blue. The other alternative we can have is, no, there's a 4-colour one. What? CMYK, okay? Intensity, cyan, magenta, and black. That's how your printer actually works. The three together, high intensity, FF, FF, FF. Is that black or is that white? If I take full on green, full on red, full on blue, is that white or black? I might put some money on it. I've got some cash here if you want to put some money on it. So,
why is it black then?
well, why is it white? You said white? You said white? You said white?
Yeah, why?
Yeah, that's right. You agree? So you take the lights together. If you've seen the demo, I should have brought the demo along. The red light, green light, blue light. Shine them together with equal intensity, and then where they meet, you get white lights. Okay. So you get sodium lights. That's because there's too much yellow, or yellow is green, red and green together. So FF, FF, FF is white, and 00000 is. And FF0000 is no red. Okay, they go red, green, blue. Okay, what's EE? I know it's a mobile phone network, but what's it? What is EE? Orange? No, that's a good answer. That is a brilliant answer, actually. That we set that one up earlier. That was it's a mobile phone joke, so it's all right. That was one of the best answers that I've heard for a long time. That was class. Did I just come into your head? Because the first thing you said, I go, no, it's not orange. That's not orange. That was a really great answer, actually. I hope everybody got that one. That was really funny. So what's DD? You're going to come up with one for this one? What's DD? I know it's one of the Ramones. That's the. But what's DD? It's grey. That's right. Yeah, not 50 Shades of Grey. That would be bad. But it is a shade of grey. It's a shade of grey. Okay. So when you get down to this level, you actually need to know your colour sets and your pixels and so on. So that's what our pixel blocks looks like for our image. That's what an image looks like zoomed in. Okay, so this is what happens with it. Basically, we take a frequency type analysis. We look at spatial frequency. If you look at this box over here, that's really what happens. See the box at the top left-hand corner? That is no change at all. The one at the bottom there is the highest change, like a checkerboard for that pattern. So we try to match the intensity against each of these little blocks there, and then we convert it. Okay, so we get a whole bunch of numbers like that. That's what they actually look like. Then what we do is that we just we filter them out, and then we divide by a certain number. It sounds like one of these games that you have, like double it and add one, and then but we do that. We say, right, who cares? You're not going to be able to see something if it's a certain amount. So we kind of divide it out. And then our result actually has a whole lot of zeros in it. Because we've said there's a threshold, not going to be able to see that. Then we end up with a whole lot of zeros. Then what happens, actually, we store them zigzag. That's a good way. And then at the very end, what we do is we store the zeros by saying, well, it's 50 zeros. And that's it. So we don't have to say 0, 0, 0, 0 50 times. We say it's a 5, a 6, and 50 zeros. And that's the way that we can actually compress actually down. So we'll come back on to Huffman coding and run length encoding later. But JPEG is quite, you can spot it a mile away. What we want is to be able to dip in anywhere and say, I think that's a JPEG. I think that's a GIF file. So we've all came across magic numbers. So you all know the magic numbers, roughly. Not the band, but there's a little header there. And there's usually a trailer there. But sometimes, within other things, anti-forensics will actually trample on that because they don't do anything. They're just there for show. But you can trample on GIF, and you can trample on the end thing there. In JPEG structures itself into blocks, and there's information in each block. And the blocks are normally these tags here. So there's the start of a frame, the end of a frame, FF, C4, FF, DA, and so on. And there's even one that, just in case we have got an FF in the file, which can happen, we need to stuff, we need to do some stuffing. So this is our stuff to say, actually, I really wanted an FF. This isn't a tag, this really is an FF. If you look at it, I've identified for this JPEG, look at the squares there, and those are the FF tags. So you can see by analysing the file, if I see lots of these FFs, there's a high probability that what I've got here is a JPEG. Even though somebody, it doesn't look like it's a JPEG, that looks like a JPEG. And when you actually analyse it, this is, you can't really see it from here, but if you analyse it, virtually every 512 byte block has at least one or two of these JPEG tags actually in them. So in that way we can actually see our content. Okay, so there's an example there. We can see that most of these sectors, the little file 512 byte blocks, have an FF something something actually in them. Okay, so this is used in triage in digital forensics. I can grab, say you've deleted the file, and it just gets deleted as it goes along. You've still got one fragment left, and I pick off that fragment there, and I can't see the magic number anymore because it's gone, the first one. I can actually identify that that was a JPEG. If I've taken the thumbprint of that little block, then I can actually say that that JPEG was, that fragment was probably part of the overall image. So that's the research that we're doing here just now as part of our research. We're trying to create little thumbprints for each of these little segments, so it's not like a whole hash of it. And what we're also trying to do is to be able to classify the fragments. If I take a little sample and say that's a GIF or that's a JPEG or that's something else. So it's quite a challenge to actually do that, but for some of the ones like JPEG, it's quite easy because they kind of give the game away because they're putting lots of these tags in there. The other one that kind of gives the game away is MP3s. MP3s are structured so that they have a bag of audio samples together. It's called a frame. Okay, so you have a bag of these, they get delivered and they get buffered and played, and then another one, and so on. So if one goes in error, then it's okay because another one will come along later. The header for an MP3 frame is 12 ones together, and that's an MP3 sync. So no matter where you go in a file, you might just dip into the middle of it or the end. As long as you find the first sync, then you can start to sync your audio from there. So this identifies itself, and you can start to look after the 4 ones to make sure it does make sense. So this was really outlined by Simpson Garfinkel. Simpson Garfinkel is the leader, the thought leader in digital forensics. He's really set out the roadmap for the next 10 years or so. And he identified that you can actually identify an MP3 file purely by finding the 12 ones. So this is an example here that I've taken. And you can see there, virtually in every one of these little fragments, I can find 12 ones together from them. So these things are the discriminators. They're giving you the heads up on roughly what's in the content. So one of the crudest methods of hiding within an image is what's called the least significant bit hiding. So the least significant bit is that I've got red colour. So let's say the colour is 120, which is about halfway. You agree? Be half of red. But I just make it 121 or 122. Do you think your eye will be able to detect that change? Can you tell the difference between that little change in red? No, it's impossible. So what we do in steganography, if we're hiding within an image, is that we modulate or change the least significant bit in it there. So there's our image, and inside this image, this is the pixels and here, and these are real colours. Can you tell the difference between each of these colours? Are they different in any way? but they are, because I'm changing the green slightly from RGB, sorry, the blue. The blue from 50, 51, 51, 50, 51, 50, 50, 50. And now again I've sent the letter H. That's 0, 1, 1, 0, 1, 1, 0, 0, 0. So if you know where in the image to look, let's say we'll do it at the start. So this is the bitmap here of this image. And what I've went in, and then I've went in and changed the hex values in there, and you would never tell. So you never be able to tell that I've actually modified it. So only by analysing it, by saying that's a bit strange. This is meant to all be white, but you're just changing the ones and zeros, and there could you actually analyse it. So normally what you do is you do a frequency analysis to see where you've got fast changes to. You can also do it with audio. If I just modulate the least significant bit of your audio wave, you're never, ever, ever, you're dealing with a 24-bit converter, you're never going to hear any difference in there. But if you look at the binary data, you can actually see the ones and zeros actually change. If I change the most significant bit, would you hear it? A better chance, you would definitely, it'll go bang. I don't know if you've ever heard like a proper glitch. It's all filtered, but the change of a most significant bit, you'll hear a bang, because it will change from one level to the, be quiet and then be loud straight away. That would never happen. Changing the least significant bit, you'd never, there's so much imperfections in the audio and so on, you're never going to hear. So you can hide it within the least significant bit of your audio and also for your video. But you can also hide it within inside the actual blocks within inside the code. Okay, so this is my dead cat again, and I've hidden a message in there, and you would never tell from the top image. That doesn't look too much like the bottom image. She's looking a bit grey there, but I've hidden an image in there, and you can see the cat has been changed. And the reason for that is that GIF has what's called a global color table. This is the header here. There's a few things here. And then within here, there are 256 colors that are going to be used in the image, each of 3 bytes. Okay, so at the top of your GIF file, you've got the little header, and then you've got the global color table. So would I use GIF for a photograph? If I had the choice between GIF or JPEG, which one would I use? Okay, so GIF has 256 colors. Okay, each of the pixels will say color 5, color 10, and so on. So would I use GIF for a high quality photograph? Why not? Is 256 colors enough to represent a high quality photograph? No. So that's the reason that GIF is used for like simple images, like simple clip art type things, because they've only got 256 colors in them maximum. JPEG, you can get any of the 24-bit colors. So you can get any color you want, the 24 bits, you have it, it's yours, but you can only have 256 of them in there. So this is the color table in here, and all I've done is I've put the word hello, which is obviously modifying the colors that were there to be a different color. And you can see in the second one, it's made quite a radical difference, because I've overwritten a colour, let's say the black in the cat's fur there, and it's went and changed it into a grey colour. So it's possible to hide things within inside the blocks that we have, and this is hiding it within inside the colour table. But there's been a whole lot of research done on investigation of printers. And I don't know if you know about it, but if you send a message from your colour printer and somebody comes to investigate that message, then they'll find out exactly what printer it was sent from. So the EFF cracked the Xerox code. They haven't managed to crack all the other ones, but they had proven that each printer is putting little yellow dots on the page. So you can see, in this case, there's the dots there. When you zoom into the image, you can actually find and identify the printer from them. Okay, so that shows one example of making something so small that you can't actually see in them. Let's see if we can get the video here. Is it going to run? Just watch the video. Don't watch me.
Somebody want to buy a Coke.
Yeah.
Coca-Cola.
Yeah. Did everybody? Did you see that one? Yeah. So that advertisers have known that technique for a long time. I could have made it really fast, and you would have still seen it. Well, you wouldn't have seen it, but your brain would have certainly seen it. You go, oh, yeah, Coca-Cola. I bet you'll go and buy Coca-Cola tonight. After that. So that's the subliminal, is that you can actually, and there is a limit where it becomes ethically really quite bad, that you actually go bang, bang, bang. And we've all done it, because you watch it. You go, oh, it's there, I'm watching it for it now, and so on. It happens so often, and you don't see it. It's a standard marketing technique. Just do something, and then just flash something there, and you won't actually see it. And then there's little codes and messages. So if you grab your phone, you've got a QR code, reader on your phone. I don't know if you want to quickly install it. If you've got a connection, can you install Zapper? Zapper, it's a Scottish company, a great Edinburgh company. So install Zapper on your phone, and let's see what we get. I'll just find my Zapper. Okay, so it's got a yellow. It's like that. It's like that logo from there. Isn't that fantastic? Oh, it's the video of this lecture. Before it even happens. No, it's not. It's a video of another lecture. Could you install Zapper? The Zapper is the one on the left-hand side. No, bro, your phone. No phone. You want my phone? Not my phone. Did it work? Zapper is an amazing technology. Imagine you can go around the supermarket and there's each logo can be branded. You go around and you don't have this. The QR codes are really quite difficult sometimes, but you generate your code. In this case, it's a URL, but it could be anything. It could be a video. It could be anything. Did it work?
Yeah, I'm here.
See? Oh yeah, so you can click on it, and you can click on the video, and it should work. Okay, that would be great to actually have done.
So I'm not gonna upload. We're not gonna upload the video.
What?
We're gonna tell them to find it on the slides.
Yeah. So could you have a shot of the QR code one? If you've got a QR code, just go ahead and install a QR code reader on it. So this doesn't quite look like a QR code, but you can spot a QR code a mile away with the little registration areas. I must admit, it's never been that reliable. I don't know if anybody really uses them that much. Do you use QR codes that much? They look great, but they often struggle. Did anybody manage to get the QR code to work? That's great. So you'll get that, and then just give it 4 seconds or so, and then it should go to a security site from there. Did it work? Yeah. Is it working? That's right. Did it working? So it's a bit difficult to hide your QR codes, obviously. But more and more that they're kind of hiding, they can hide them with inside, or they can create like proper images that you can actually see from there. Did you manage to get that? Got your zapper? Is your QR code not working? Yeah. Is it too far away? Should be okay. It's quite big on the screen. We have tried with the normal type ones, and they don't quite work if you don't zoom them right up or from a data projector from them. That work? No, it's okay.
Yeah.
Right. What time do you make it?
It's 10.
10.
So,
Yeah. What we'll do is we'll have a break for 5 minutes, and then we'll do some scalpel, we'll do some file carving, and we'll do some port knocking and Tor routing and so on. Okay, thanks. Right. Okay, so we'll make a little start again. So on the online version of the lecture, I'll give practical demonstrations of file carving in action. I don't think we've got time today to actually do the live demo, but if you watch the lecture back, I'll show you how you can carve out files, because sometimes what you have is like a whole lot of data, and right in the middle of it is something that you're interested in, like a file. So file carving is used to be able to carve out files from your data. And so what we often look for is we've got our header. We have a header for a GIF file. It's obviously GIF 89A, as we've seen. So if we scan the disk, the minute we hit GIF 89A, that's the start, and then we carve as much as we need until we get to the end, or until we run out of what we think is the maximum size, and we carve that out as a file. Whether it's valid or not is to be seen. So these are some of the headers that we look for. These are the hexadecimal values and some of the other things. So for a JPEG, we look for FFD8FF. That's the start, and so on. For a PDF, we look for %PDF, and that defines the starting point. And then there's normally a trailer that we actually look for. So we get some more complicated sort of signatures, like there's one for a PST file. If we see that in a network packet, that's a really bad. Or if our snort detects this BDN file, then we know that somebody could be transferring an Outlook post office off the network and so on. So we use this for a network scanning and to be able to pick things out. Okay, so there's a more complete picture of these magic numbers there. There's a RAR file in there. AVI list is a typical thing if we're looking for an AVI file. Okay, so there's an example of a JPEG. Okay, so with our JPEG, hello, that's fine. So with our JPEG, we have FFD8 as our starting 2 bytes in it. And we also see typically a JFIF header file which contains some of the metadata within the file. Okay, so there's the example we've seen earlier. We can actually see there is a GIF file within our PowerPoint. So if we wanted to carve that out, then we'd identify the starting element of it. So you probably find the GIF header is somewhere around here, and then the file is within it. Okay, there's a zip file. So a zip file always starts with 04, 03, and so on. And we can actually start to carve out. The interesting thing about a zip file is that all the names within the GIF, within the zip file, are shown even if it's password protected. So it doesn't hide the identity of any of the files within the file. So one package we can use in terms of carving out data from any data that we've captured is Scalpel. So Scalpel comes with a configuration file. So this is an example configuration here. So what it looks for is a header and a footer, or it looks for the maximum size of the file. So what can obviously happen is that you've got the start of the file, you've got the middle of the file, but the end of the file has been deleted, which will mean the Scalpel will just keep loading all of the data. So if that trailer doesn't happen, then we can actually define the maximum size of the file that we want to actually carve. Hopefully we'll find the end of it, but if we don't, then we might end up with almost a massively large file. Okay, so if you could have a look at Scalpel, we've got some examples. Simpson Garfinkel, again, as part of his site, has set up a whole lot of test data that you can actually carve things out. So he's got photographs from cameras that have been deleted and has taken an image of that, and through Scalpel you can actually extract. There's been lots of research done about buying phones on eBay, and they actually look, you think you've erased the whole of the camera, you use something like Scalpel, and you actually find that they're still there and can be extracted quite easily from the phone. Okay, so increasingly, like in digital forensics, this is the methodology that they're using in terms of quick triage. So if you quickly want images out of a disk, then you would run a tool such as Scalpel across the disk, and it will just extract all the things without actually looking for things, because people can change the file extension and you think, oh, there's no JPEG there, but actually they change JPEG to a .bin file and then make it a system file, and EnCase won't actually find it. So these tools are used increasingly in terms of triage. One of the most extensive tools that's actually used in our data representation is Huffman coding and exclusive OR. Huffman coding tries to be as efficient as possible. So virtually much of the data that you have, images and video and so on, is actually encoded into Huffman. Huffman takes the probability of a character and gives it a very short code. Because what we're doing is we represent what's the least probable letter in the English alphabet. Z or a Q, something like that. Any letter that's got a 10 in Scrabble. And the most probable is an E. So Huffman said, why don't you represent an E with a really short code? Let's call it 0. And a Z will be 1110001. Let's make it long. And we can actually compress the whole of the stream down massively by making the length of the code linked to the probability of the actual occurrence of the letter. So this is how it actually works. So we've got occurrences there. What we do is we arrange them in their order. So you can see the E is more popular than C, and so on. Then what we do is that we arrange them down like this, and we put the occurrences of each, and then we give the least most probable a 0, and then the next highest one a 1. Then we do a total of that. Then we see if that one's greater than that, and it isn't. So then we say that's a 0 and a 1. And then we'll bring them together, and then we've got these two together, and a 0 and 1, and so on. And then we read the code backwards. So in this case now, an E is represented as a 1 and a 1. An I is represented as a 0 and a 1. You can see that we end up with codes like this. and we can put them all together and they automatically synchronize. So can somebody read that message there? So now we don't need our 8 characters together. Can anybody, so we start from here. What does that say? Or what are the letters? Say that again. P. P O E. You agree? So there's no need for synchronization and so on. You can, every bit that occurs, like if a 0 comes in, then you know it's not an I or an E, and then another 0 comes in, then you know straight away it's an O. Okay? So this is what's used. This is why a GIF file is so small. This is why a JPEG is so small. This is why our data generally is so small that we actually have a table at the start of the file that actually says that an E is going to be encoded with a 1-1. And it massively reduces the size of the file. And obviously we can use this for steganography because we can start to represent our data in terms of a very short code that you would really never identify from them. So that's that. And obviously we've seen before our exclusive OR. So the great thing with exclusive OR is that if you exclusive OR something twice, you end up with the same thing back again. So exclusive OR is a great operator for that. So in this case I've got a message called Napier and I'm using an exclusive OR operator of T. So it takes each letter, exclusive ORs it with T. So a 0, 0 in exclusive OR gives us 0, 0, 1, 1, 1, 0, 1, 1, 0. Okay? And the great thing is that we do that twice with the same bit and we end up with the same original bit. So nothing gets lost, but the message gets completely scrambled, completely. So we take a T, there's the bit stream there. We do it back again and we can get the message in there. And the other one we use is rotate left and rotate right. So if we rotate the bits, then the bits go off the end and come on the other side and so on. Both of these operators are what we use in cryptography because they never lose anything. As long as we know how to do the reverse of it, and to do it in the right sequence, then everything's actually fine there. So exclusive OR is great, and that's what we used for our cipher that we won this year. We just used a simple exclusive OR to hide the magic numbers because there's a magic number in there and we wanted to hide it, so we just used an exclusive OR FF. What does an exclusive OR FF do to each of the bytes? If I XOR each byte with an FF, what is it really doing? Inverse. Just flips all the bits. That's enough to get people off the track. They're looking for GIF and MZ and PK. You just flip the bits, and it comes out as something different when they look at their hex viewer. Okay, so those are the two important operators. Obviously, why have I used base64 format to represent the encoded string? Because normally what we will end up with is non-printable. You can't really send smiley face, bing bong, new line as a message. So we typically convert it either to hex or into base64, and that will work. It's easy for us to convert it back if required. So probably the award for one of the greatest contributions to saving data and really helping us hide things is LempoVis. You also get LempoVis Welsh for LZW. Okay, it's a standard compression technique that's been used for years. Been around and it works really well. And it's based similarly to Huffman, but what you get is that it will scan the system looking for a list of words, say in this case, and then it will allocate each of these a number. So it's taken the boy stood on the burning deck, the end, and then it creates a dictionary. So this is the dictionary here. And then let's give each one an index value for it. So in this case, we've only got 10 different values in there. So we've taken a space, a dot, an end, and so on. And then what we can do to actually store this is a T, that's there. This is a space, that's there. This is a 3, which is, have I got this right, which is stood there, and so on. So you can see now we've already reduced it down, and just by referring to the table. And this is what happens in images. Because when you're watching a movie, actually, that bit there is the same as the bit next, same as that bit, and the same as that bit. In fact, that bit appears all over the screen. There's very little pixels change between one frame. Video, I hate to say it, is just like a flick book. It's like a flick book. You don't see it. It's like one image. It's not quite like that. Does anybody know how it differs? So TV is like moving pictures. I know that sounds a bit strange, but it's just basically one picture comes in. But that would be too fast for it. Does anybody know what really happens? So that's what's called the main frame. That's the Q frame, the key frame. The key frame gets transmitted. Does anybody know what happens next? When you've seen your TV glitching, does something kind of happen? You're watching a football match, and something kind of strange goes wrong. You can see the ball going a bit strange. Do you know why that? What causes that? Well, basically, you get intermediate frames that are just. This is the update. The ball has moved here. So all I need to do is to change. I need to say just change that bit of the screen to that one. But obviously, you might lose synchronization. So every so often, you need to transmit the whole thing again, just because you have to start. So that's what happens when we look at our compressed TV. You get the full thing, and then you get little intermediate things. So you can see here, actually, and look at that wall there. There's only one little thing that's actually changing there. So in Lempo Viz, what we have is we say it's actually that, and that again, and that again, and then occasionally we'll get this one here. That's a different one there. And then what we can do is we can actually say run length encoding. Let's have 4 of them, and then a 2, and then 5 ones, and so on. And you can compress it down, and we can hide our message in there. So this is the core of a lot of video, a lot of image, a lot of audio is really this Lempo Viz type method. Another thing that we have is what's called the zero knowledge problem. And so the zero knowledge is that we've got they used to call it 2 millionaires. We'll call them 2 billionaires now to take into account inflation. But we've got 2 billionaires, and we do know who's got the most money. Who's got the most money?
Bill.
Bill, by quite a long way. But Richard is quite rich too. Doing all right. Doesn't even live in this country anymore. So he's doing that well. He doesn't even live here anymore. So so they get together, and he doesn't want to tell him how much money he's got, really. So how do they get together? They talk openly, and at the end of it, Bill says, "I've got more money than you." And that's what's called zero knowledge problems. How can we create something that we can give some data away, but we don't actually give away the core data that we're actually trying to protect? So it's a bit like I don't know if you've seen the wireless auctions that happened in the US. It was crazy. So you know how each state will bid for the contract, the mobile phone provider will bid for the wireless contract. The first few were brilliant. The states got lots of money, and because all the wireless companies were competing against each other, and it was meant to be that it was secret, the bid they were putting in, and then they realised they could if I go really low on this one, and someone else will win that one, and then they'll win that one, and then I'll go in high in the next one, and then everybody else will go in low. And they actually found that the actual price of the contracts went through the floor because everybody started to play the game. They honestly didn't tell each other, but they all knew, I'm going to go in low in this one, and then let's go in high for this one, but don't go in too high if you're competing in the normal way. So in that way, they didn't actually know what the other bits were, but they could play the game. With zero knowledge, in this case, it will typically be used, say, for an online bidding system where there is no Trent. So normally in cryptography we have Trent. Trent is there to be trusted. So Trent would talk to Bill and Richard and say, tell me how much money you've got. And then Trent would say, well, Bill wins. So that's a trust network. In some systems, we can't trust anybody. Okay? Typically in something like a bidding system for something, you don't even trust the person who's controlling the bid. You want to put your bid in, but you don't want to show anybody what the value of your bid is. So one of the protocols that we've got, and this is an example that you can have a look at online, and in this case, Bob, Alice, and Carol have some votes. So Bob has voted 2, Alice has voted 2, and Carol has voted 8. What we want to find out is the total number of votes in the whole system without us asking Bob, Carol, and Alice what their votes are. So you can have a look online, but basically there's a few calculations that they do, and they do the calculations, and at the very end, it ends up with the actual value of the total number of votes without them ever actually saying what their actually votes were. So these are what are called zero knowledge problems from there. So another area that we have in steganography is port knocking. And port knocking, as I said earlier, is really the ability to get access to, say, a service or a data channel where you connect in a certain way and it'll open up a certain port. So there are well-known tools around, open source ones, that allow you to actually do that. So the port that looks as if it's open is 99, or it isn't open, but you send a signal to it. You then send a signal to 199 in this case, and magically a new port actually opens that you can actually connect into from there. The area that we've been working in here is what's called secret shares. And secret shares is a bit like the pirate problem. So the pirate problem is that none of the pirates really trust each other at all. But they want to store the map with the X on it. So the problem that they have is obviously if they cut the map up into bits, whoever's going to get the X is privileged from that. So a secret share is really where all the pirates will be given a share, and then you define the minimum number of pirates that are required to bring their shares together to rebuild the map back again. Okay, and it was Shamir, Aldi Shamir, that came up with the algorithm, initial algorithm for this. And he defined a method to say any k thresholds, that's the number of data elements that need to come together, for an n number of shares. So this example here, I've taken the message X marks the spot, and I've went from any 2 from 4. So it's possible for you to take any 2 of those shares together and bring them back to reveal the original message. So we're looking at this in terms of striping across a cloud. So I could have 4 different cloud providers, and then what I could do is take my data and then I could split it into 4 shares and then do any 3 from 4. So if one of my cloud providers fails, then I can still build the data back again. Can anybody looking at my clouds determine the original data? Okay, so I've put my data into the 4 clouds. There's no cryptography in here, no keys or anything like that. I've taken my secret shares, I've said any 3 from 4, and I put the shares into my clouds. Can anybody looking at any one of those or any 2 of those get my data? No, they can't. And it's based on simple mathematics. If we've got a secret, which is the equation of a straight line, if I give you 1 point and I keep 1 point, then even if you look at the points that we have, you can't tell what the gradient of the line is. Only by bringing the 2 points together can you actually show the straight line. It gets more complicated. You've got to draw a quadratic equation, and you've got to do really complicated equations, but it all kind of works out. So we're looking at this in terms of robustness. What we'd love is a self-organizing disaster recovery system, and we think it might be possible where you can just throw all the shares down and the whole thing crashes, your whole cloud, everything, the data. And have you ever seen The Sorcerer's Apprentice, where he kind of chops it up into little bits and he thinks he's got rid of it, and then all the bits get back together and they'll get the... It'd be a bit like that. They can all get back together and they can all build the system back again. If you examine any one of the shares, you can't actually release anything. The one thing that this is missing is what's called a break glass. So a break glass is that two of the pirates have actually died, and they go, fair's fair. They're dead, they're not going to come back. Let's do a break glass. Let's have something that we can have a 2 from 3 rather than a 2 from 4 rather than a 3 from 4. So that's one thing that we're looking at just now, is a break glass policy. Two pirates die, and we can still get two pirates to come together, really, but they've got to have a special... You've got to prove that the other two pirates are dead before that can actually happen. So we're looking at this like in things like healthcare. So your GP record, you could have one part and the GP could have the other part. Only when you go and see the GP and he brings the data together does the data come up. The data there, you can change it, and then you take your data away and he can't see the record. Okay, so it's possible when you bring in another stakeholder, such as the family or a social worker, and you can actually start to say 3 out of 4 people can come together and actually rebuild the data again. And the great thing is it doesn't involve keys. It doesn't involve any encryption keys or anything like that. Because as we know, the whole thing is a shambles. PKI is a disaster area, and things need to actually change. And the other thing that we have with steganography is that we're really trying to hide the original source of the data. When I was an electrician at one time in a chemical factory, so one thing that we used to do when we were working on the plant was that you'd have an isolator, like you know how you get like a fuse box. You've got an isolator that you isolate something. What used to happen is there was lots of people working on the equipment, is that you used to put a hasp on. That's the hasp there. So you would lock it closed, you'd put a hasp on it, and you would put your padlock on it. So anybody who was working on the actual plant would put their own padlock. So you could take your padlock off, and they still couldn't put the power back on. So only when everybody had taken their padlock off would it actually... Have you seen these things? Have you seen... You got a kind of... Okay, so onion routing is really like that. So the Tor network hides the entity and all the entities by each entity encrypting with their key. Okay, so we can see the colored keys here, there. So there's the website over there, and Bob initially uses the 3 keys from the root. So in a Tor network, any device is a routing element. So they don't use the normal routing elements that you would get. They use your PC, you use your phone, whatever. They will use that as a routing element. Anybody who's part of the Tor network, you become part of the routing chain in there. So we've selected 3 for our Tor connection here. So this one has a red key, green key, and blue key. So initially, Bob takes the data. He then encrypts with the blue key. He then encrypts with the green key, and then encrypts with the red key. So can I decrypt that with the green key, then the red key, then the purple key? No. How do I have to do it? Red, then green, then purple. Okay. So we agree. I did show you once there is another method to do it, and you can go onto the site. There is another method to do this where you can take the keys off, but in normal cryptography, that's the way it would actually happen. So Bob, when he's accessing the website, sends it with all the encrypted keys, because when he creates the connection, they all return back their keys back through the Tor network. So he sends it on to the first routing network. I've shown it around the wrong way. Sorry, it should be blue. It should be blue. Sorry, because of that one. Imagine it's blue. So the first routing element takes its key off, takes its padlock off. There, I've shown that. I'll make sure the slides are updated. So it will take its purple key off. You're not colourblind. There's no, I can't trick you that way. It takes the purple key off there, and then it'll go out to the next one, and then the next one should be green, but it should be red and there. So the next one will take its key, its key off. It's encrypted. It'll decrypt, and then the last one should be red. It'll be red here, and then it'll take that one off and down. So tell me whose IP address will appear. Tell me, just tell me whose IP address will appear Alice's website. The last one. And will the data, if I listen to the communication between the red node and Alice, will I be able to do that? Yes. Okay. So the last part of the Tor network is unencrypted. All the other ones are encrypted. If you manage to become the chain, then you have, and that's what happened. Some researchers in the US managed to sit long enough in the network that they became the chain. If you can provide every node in a chain, then you can now own all the keys. They did it, and then they pulled the paper. So they were going to present at a Black Hat conference, and they pulled it completely. Because ethically, is it right? You tell me if it's ethically right to sit in a Tor network, which is there to preserve privacy. Is it right or is it not? I'll leave you to think about that one. We all know the bad things that go on. It's not the fault of the Tor network or the Tor protocol for that to be done. And this is a perfectly valid routing method to keep your data secure. It's an excellent method because it's onion skinning. And even by knowing one of the keys, you can't actually determine the data in there. But if they manage to get in there ethically, it sounds a bit strange. So they pulled the paper, but that was the method that they actually used as part of that. Okay, so that's how someone hides. What's another method you can hide your anonymity? What's a typical method that someone uses to hide the original source? Was it spoofing? We can spoof, we can pretend to be certain servers and so on. What's an even more typical method? Ward driving is obviously one. It's not so easy to do ward driving anymore, but someone, with so many guest networks now, someone will go on site and then use the ward drive from that site. But what's the typical method that someone would use to hide their original source? A proxy. So a proxy is the typical method, and a compromised node is like a proxy. So for most denial of service, it's actually compromised nodes that are being taken over on a botnet that are actually doing the attacking and are attacking by proxy. Okay, so that's onion string, onion routing in there. Another method that can be used in terms of keeping our messages secret is a covert message. And a covert message is where Mallory is watching Bob and Alice, watching everything they're doing, and Bob and Alice need to find a way to be able to pass the message without Mallory actually seeing it. So as I said earlier, if I stick my hand up every minute, or if I not, then that is a way that we can pass a message. That's a signal, and that's a timing signal. So if I every so often we know that the signal will actually be passed. So we can either have a timing channel, so we do something at a certain time. So let's say we throttle the CPU on a server. I make the server do something, and that's a 1. If I don't make it do something in an hour's time, that's a 0. So you can see there's an infinite ways that I can pass a message. You sit and watch your server. If it goes up to 100%, I give it a little crypto stuff to do. Then I'm passing you a 1. If it's not, then it's a 0. Or we can have a storage channel where we can actually store something. We can start a process off at a given time. And with inside IP and TCP, there are lots of places that Bob and Alice can hide things. And there's such bad protocols. There's so many horrible things in there that really don't have to be there, that really aren't necessary. So an area like Time to Live, can I put a character in there? Would it work? Can I put hello, H-E-L-L-O? Would that work? How many bits? No? Small? 8. So if I sent you one character at a time, would that work? That would work. That would work. But as long as you knew I was doing that. So I could send hello in the TTL. What do I need to avoid? Why does the TTL even exist? What? Number of hops. It's decremented by every device into intermediate device. I've just got to watch it doesn't drop to 0, or what happens when it drops to 0? It'll stop, yeah. Usually there's just a few hops these days. There's not maybe 3-4 hops to go anywhere in the world anymore. It's not really going to happen. So I can stick my message in here. I can stick my message in the identification. Nobody really uses that in there. I can stick it in the fragment offset, whatever that is. We used to use fragmentation for IP packets. That was killed long ago. Nobody would ever allow IP fragmentation. In the TCP area, we've got urgent pointer, whatever that is, and we've got data offset. So people can actually hide message in your packets. They're looking at your packets and they're going, everything's fine, the messages are okay, but actually someone's hidden them inside the fields inside it. And it's not too difficult to do that from them. So this is an example from, are we going to be able to see this one here? This is from an Israeli website, an Israeli security website here. Just having a look at the ISN. So the ISN number is the initial sequence number for the TCP packet. Okay? So that's got to be random. As long as that's not the same value as what's been previous in the last 10 minutes or so, you're okay. So as long as the value is fairly unique, then you're not going to get mixed up at all. So this is what the ISN number is kind of meant to be like. It's meant to be written. It's meant to be fairly variable like that. So that's taken it from, that's the sequence number of the packets. But when you actually look at it, nobody wrote this down. Nobody said in the TCP spec, if you read the RFC, nobody says you shall calculate the ISN this way, and you will make sure that you add 1 onto it each time for each packet. Nobody actually really said that. So all the operating systems wrote their own stack in their own way and actually defined it. So if you look at Sun Solaris increments the segment number and then all of a sudden jumps. Okay, so you can actually see here, all of a sudden it jumps and it changes a value and then increments for the TCP segments and then does and so on. Windows just seems to quite happily just increase. It'll start with a random number and then it just keeps increasing from there. Linux is probably doing it right. It's doing a few and then it's jumping and so on. And OpenBSD just quite happily just potters along there. So actually you can fingerprint the operating system type purely by looking at the way that the identification number of the segment actually goes. And you can pinpoint the difference between Windows. Oh, sorry, it's gone. So every so often it just takes a big jump from there. And some say that people have been using this. I don't know if you ever heard on the people have been using radio channels. I don't know if you've ever tuned into a channel and there's a kind of strange, you can hear Morse code or something. So security agencies have used this for many years. There's a certain frequency that you go to, and if you listen to it, they're sending messages. So this is an example actually of there's a covert channel being set up there that we've actually modulated, intentionally modulated the segment number to send the message. And the one at the bottom is a real site, and we think they were sending covert messages there because that just doesn't look right in terms of the values actually in there. Okay, so you can fingerprint and you can even send your secret messages within that. You can have a look online, but this is an example of where it is jumping. So there's the identification number. This looks like a Linux type system here. Identification number goes there, and then it takes a jump up to the 109. So I think that's a Linux one that's doing that jump. This is Solaris one. Have I got that in there? Solaris from them. Yeah, and you can see this one here. So there's the increment, and then it's jumping from there. It's going from 5702 down to 80, 81, and so on. So it's a fairly regular, and you can really fingerprint the actual type from there. Okay, so there's a whole lot of other methods. Can anybody think of any other methods that somebody might want to use in terms of hiding information? There's an infinite number of them. Is there any method that you would like to go into any more detail of? Was there something that didn't quite see? So I'll put some examples online that you can actually have a look at real examples, and I'll let you have a look at the code that we created for the cyber security challenge. So let's not try and find where I put that. Let me find where we are. There we go. Do this in Internet Explorer. Right, so this was our cipher code. So everything looks fine in there. But what we did was that we took an exe program and we split it up into three. So we took the whole exe. And then if we wanted 3 bullet points, we chopped them into 3, and that gave us our exe. We did an XOR, we did a compress. The XOR was there to hide the magic number for the compress file. We brought in the header of the GIF that we saw earlier, and then they become bullets. So this page actually contains an executable, but you would never know that. So only by knowing that that you can actually take the bullets off, and there could be many of them in there, would you actually know how to build it? And I'll just let you see the cipher. Our cipher, just trying to find where I put it. Dark source cipher. Here we are here. Okay, so there's the 3 GIF files that we've actually created, and we've taken an original file called hping.exe. So there's our hping. It's just a nping, sorry, nping. Okay, so we took this program and then we processed it so that we created the exes, and then we put the GIFs into the page. So I'll just show you that actually doing it. So I'll erase the GIF files that we've got, just to show that they don't actually exist. Okay, so there's no GIFs in there. If we take our cipher, and then we're going to encrypt, and we'll take 3 bullets, and it's called nping. Okay, it's actually created our GIF files in there. So it's taken the exe, split it into three, because we've defined three bullets, and then, as I said, it's put in a GIF header for each of them. If you look at them in terms of our hex viewer, yeah, so just have a little look. Still trying to find. Okay, so there's what the GIF files actually look like before they're actually applied. These are the GIF files as they would be without the exclusive OR or the compressed. Does anybody know the magic number that you look for an EXE?
Yeah,
MZ? Can anybody see it? Probably can't from there. But you can see our MZ is there. Okay. So if you look at this, there's the GIF. There's the color table. I've just filled it with black in there. We could fill it with any color, and then there is the start of the EXE. This is the first GIF, so this is obviously going to have the first part of the EXE. So it's the only one that's going to have that MZ in it. But any EXE will typically have text. Okay, so if we just did this, it would have been easy to crack. It would have been spotted at a mile away that this is an executable program. They would have then carved that out and then carved the other one. So what we did was to be able to go in and then exclusive OR that, and all the exclusive OR does is just flip the bits. As far as the GIF file is concerned, then it doesn't actually care that much. So then I can prove that it works, hopefully. So I'll get rid of the end ping, so it doesn't exist anymore. And then what I'll do is I'll bring the cipher back. Hopefully, it's end3 decrypt. Remember, and it's created a program called out.exe. Oops. Oh, sorry. I've put in the version I've got. Is trying to read the ones with exclusive OR, so I was just showing you that as plain there. Okay, so that was the cipher that we did. I'll let you see some of the other ones. They were quite interesting. From Raw Holloway, we had this one. Try and find it. So try and find the ciphers. Sorry. See if I can try and find them. Ciphers. Let's see if I can find Dallas. Map. Find that one. No, not having much joy with that one. Just try and find that one. There we go. It's not that one. No. It's not that one. Well, what it was a picture of Alice in Wonderland, and they had modulated the least significant bit on each of the colours to be able to put in a URL that you actually went to from that. Okay, so that was a little introduction into steganography, and as you can see, there are so many different techniques that are possible to make this happen. Okay, thank you.